Welcome to running chemistry experiments in Makya. This isn't about replacing your chemistry, it's about enhancing it. In this session, you'll see how Makya lets you run experiments the way that you already think, while integrating generative AI to drive faster insights, smarter decisions, and fewer dead ends. Unlike typical Gen AI models that just generate smiles or optimize black box scores, Makya is built to think like a chemist. It understands structures, reactivity, and constraints at the building block level. That means we can ask chemically meaningful questions like, what if we replace the cyclobutene tail with synthetically accessible alternatives? What if we substitute the head group using specific name reactions? Or what if we explore new heterocycles by hopping out the core under structure constraints? Let's dive into our first case. Here we are targeting the cyclobutene tail in the reference ligand. Using Makya, we selectively grow new molecules tails at this position starting from a carboxylic acid and a chemically relevant fragment commonly used for amide formation in medicinal chemistry. In this example, we've set rules that only allowed building blocks with 0 aromatic rings, exactly 1 hydrogen bond donor, and at least 1 spiral atoms. This ensured that every molecule generated stay within the chemical meaningful space, synthetically accessible, structurally novel, and aligned with the project's design goals. And as you can see, the outputs only spiral containing analogs targeted control diversity with non-manual curation. All right, let's jump into our first case using Makya. The first things that we do here is define the starting fragments and the exit vector, which is a carboxylic acid, as you can see here. This is a chemically meaningful point of growth commonly used for amide coupling in real-world synthesis. So this is where we tell Makya to begin building. Next, we move into the building block modules. Here, we define the physical chemical constraints that we want for our building blocks. Specifically here, I'm setting the number of aromatic rings to 0, so no aromatic groups are introduced in this tail. Number of hydrogen bond donors to 1. We are limiting it to a single hydrogen bond donor and number of spiral atoms as minimum 1. We want to explore spiral-based diversification. Once those constraints are in, we can generate and the results can back immediately filter. As you'll see here, every molecule respects those inputs. They are all featuring spiral groups, non-aromatic rings in the new sections, and 1 hydrogen bond donor in the substituted tail. That's the power of chemistry-aware generation. We are not just hoping for good outputs, we are guiding it directly through design. Now let's look at the second case. This time we're modifying the pyridyl carboxyamide head group, highlighted here in blue. We start by selecting the growing points, in this case, the chloro-substituted handle, which is ideal for palladium catalyzed cross-coupling reaction. Again, this is a chemically valid and widely used synthetic route, not just as generic placeholder. Next, we set our named reaction constraints. We tell Makya to only use transformation compatible with palladium coupling. This ensures the chemistry is not only predictive but doable in the lab. Then we layered on physicochemical filters to define what will allowed in the new head group. In this particular case, we want molecules with molecular weight below 650, exactly 4 aromatic rings, hydrogen acceptors between 8 and 10, fewer than 3 hydrogen bond donors. Also, we've added a smart base filter to exclude paints and togs, so any molecule containing undesirable substructure is automatically filtered out. Once we run the generation, Makya gives us back what we ask for, only palladium couplings, PhysChem compliant head groups that can be realistically synthesized and aligned with the drug-like properties profile. Again, no post-processing filter needed. Everything is controlled upfront through chemistry-aware inputs. All right, let's walk through the second case in Makya. So first, I'll select the chloro-substituted position as the growing point. This is our chemically meaningful site for palladium coupling. Next, here in the setup panel, I'll add the reaction type filter, selecting only named reactions compatible with palladium catalysis. Next, I'll walk you through settings for the physical-chemical constraints in the product. This is different from building block constraints. Here, we are applying filters on the final molecules. In this particular case, we want molecules with molecular weights lower than 650, exactly 4 aromatic rings, hydrogen bonds acceptors between 8 and 10, and less than 3 hydrogen bonds donors. Also, we've added a list of smarts as pain stocks. In this way, we are telling Makya that we don't want any molecules with these substructures in our generating results. With all that said, we can move into the results and generate molecules. As you see here, the results strictly follow the rules. We get only palladium couple head groups, every one of them compliant with our PhysChem profile. This kind of control over both the reaction and the product is what makes Makya unique. We are not guessing, we are guiding. Let's move on to our third and final case, this time focusing on the core scaffold, marked here in green. In this example, we are exploring core replacement. The modification starts from two key linking atoms, both nitrogens on the core, which define the attachment point for the new heterocycles. We apply substructure constraints on the final product, which means we are not just generating anything. We are only retaining molecules that match specific structural motif. And as you can see in the bottom row, the outcome is exactly what we want. New core scaffold analogs, all compliant with our design rules. All right, now for the third and final case in Makya. So the first thing that I'm doing in Makya is selecting the linking atom, these two amine groups, which define where we'll connect the new core. This tells the generator exactly where it can link from. Next, I'm jumping into the product constraints and the level of the substructure constraint. This is a real powerful tool because here we're telling Makya to only keep molecules that contain specific substructures or functional features. Also, we'd added the smart base filters to exclude known pains and tox, so any molecule containing undesirable substructures is automatically filtered out, and the previously discussed PhysChem descriptors. Then, after launching the generator and getting the results, you will see that all the molecules are fully compliant with our constraint. New cores built exactly from those two linking points, as you can observe here, and filter in real time to match the substructure rules. No post-processing, not cleanup, just focus chemistry guided generation.